All right, thanks for the opportunity to present to all the participants today. And what I'd like to do is just talk a little bit about what's happening in the spatial digital twins area and what we see at Voxelmaps of a revolution that's happening across the environment. So if you look at what's really happening, let me just get rid of something here. It's a really exciting time, I think, for those of us in the spatial digital twin area, and a great time to be a geographer. So there's a lot of changes happening, and this whole digital twin reality capture used to be in the domain of the surveyors, and really, the professional surveyors, right? And then sensors started reducing in cost and started to be used in larger scale mapping projects. And then, the advent of LiDAR companies and new LiDAR companies coming in and giving autonomous vehicles and robots and other sorts of devices the ability to actually see our 3D world and actually capture that. And now phone manufacturers started developing consumer devices with these LiDAR sensors, so I can actually go out with a phone and LiDAR objects. And it's really creating this explosion of 3D spatial digital twin data. So it's an exciting time for all of us here to participate in this market. So quickly on an overview of our company, Voxelmaps. So we've been around for 4 years. We spun out of a group called NavMe, which is an established navigation and SD mapping company out of Nottingham, England. As Peter said earlier, we have an office. Our headquarters is based in San Francisco, but we have other offices across the globe and staff across the globe as well. So we have about 350 people across 6 countries. A lot of them are project-based and helping with some of the face-to-face data collection projects that we have. But we have a really deep mapping and geospatial and data processing experience on a global scale. So we really operate under this concept of maps for machines. And so everybody understands human maps, right? Because every day we use our phone for various purposes, and we use Google and Bing and others, right? And these maps help us navigate to a building, to an address, et cetera. And it's really visualization of a pretty broad geospatial data, but it tends to be more 2 to 2.5D data with a little bit lower resolution. And what we're really focused on is creating machine maps, right? And so these are 3D and 4D volumetric data models, right? And allow us to do analysis of multiple objects, whether it's, street infrastructure, telecom, utilities, land structures, et cetera. This data tends to be of a higher resolution. So in our model, we're storing objects from between 1 and 4 centimeters. But the key thing is not just the objects, but the measurement and the attribution of that. So we're not just tracking and extracting features, objects themselves, but we're performing that measurement as well. And there is a requirement for in terms of this whole spatial digital twin for both indoor, outdoor, subsurface, as well as underwater bathy data. So these maps for machine, for us, there's really 2 components to it. One is mapping the world, where we do outdoor mobile mapping, whether it's LiDAR and imagery, and then we do indoor mapping with backpack and fixed LiDAR and imagery. And then we also perform aerial mapping with and through a number of partners, and that's from drones or helicopter or fixed wing platforms. And then we also do mapping of people and things. So it's not really the spatial digital twin, but it's performing user studies and capturing custom imagery and 3D scans of people, places, and things, and even sounds. And so we actually had a project where we were mapping soundscapes, collection of real world audio data. So pretty broad, but again, if you think about it, it all fits within this spatial digital twin community. So we at Voxelmaps, we use voxels, and so a voxel is basically a volumetric pixel. That's the best way to think about it, and it's used in Minecraft and other computer games. So many people have used it. If you've had any sort of an MRI or any sort of a scan, done by your doctor. They use voxels in the finite analysis and trying to determine where that tear is in your meniscus. So the way that we store the data is unique. So there's other organizations that use voxels, but we use this multi-resolution voxel occupancy grid. So it's basically, just think of a megavoxel put around the Earth center, Earth-thick system, and then we as we collect data and put it into this model, each individual voxel has a position and a unique machine address associated with it. So we validate the occupancy status of the voxel. So if a LiDAR pulse goes through that object, through that bog, that occupancy grid, and it doesn't have any sort of reflectance to it, that's a larger voxel. So it's like an 8 meter. But once it starts hitting objects, utility lines, poles, trees, etc., and we start getting storing that data in smaller and smaller voxel structure. And this really creates a global geospatial database for us for both 3D and 4D data. So every voxel has an infinite series of time states, so we can do a lot of change detection. And it's a real-time, persistent, petabyte scale, 5G enabled database. And again, it's just, if you think about it, every place in the world can be associated with a particular voxel. So as we collect the data, it gets put into this overarching voxel database structure that we use. Then what we do is we use our platform, and we can use the platform in a number of different ways. So one of those is the new Symbo, which is this low-cost, small, dual-headed LiDAR collection device, right? So it's got 6 cameras. We're collecting 58 megapixels per frame, 5 frames a second. So just under 300 megapixels per second, right? And the dual-headed LiDAR is collecting it's a dual return mode, 1.2 million points per second, not per square meter. And we can drive at about 60 miles an hour and still collect good data. We do some edge processing on board that device using the NVIDIA AXG Xavier card, and then we have LTE and Wi-Fi connection with the device. So we actually, the driver actually talks to the device with an iPad, right? And very small unit, easy to put on. It's a single person install, about a half an hour, just some bolts onto a Thule bike rack. So it makes it really easy. It's not one of these devices that takes a whole team of people. Makes it easy at the end of the day to pop it off and put it in the Pelican case and take it into the hotel. Once we have that, we put that into that voxel database structure that I talked about, and then we can do automated feature extraction. And that's really the beauty of the system that we have, the platform that we have. So we can extract objects, we can do measurements. As you can see, like here in the upper right-hand side, as we extract the pole, it gives me a measurement of it. But then, as I mentioned, this whole 4D model, where we have an infinite number of time states of that individual voxel, we can go off and do simple collections for customers. So in the lower right, this was for a telecom customer, and they were only interested in locations of where the new 5G antennas had been put on poles. So, it was a way for them to monitor, the contractor had done what they said they were going to do, and it placed the 5G antenna on the right pole, right? So we had a base level data set. This happens to be in San Francisco. We did a redrive and a collect, and then just look for voxels that had changed, right? And just generated that data set for them. And so this platform that we have, on the software side, allows for the storing of the content that we collect, and whether it's by a partner or an existing data set, it could be the 3Dep data from USGS. It really doesn't matter. We're data agnostic, so we can consume all that data, then provide easy to use tools for customers to retrieve that data, perform extraction using our AI and ML technology, and then using machine learning and data conflation tools that we have on the analysis side. So it's really a very solid data stack as a software as a service for this Voxelmaps Insight platform, the VIP. So As I mentioned, we collect data from a wide variety of sources. It could be from our customers, and then we operate end-to-end mapping projects. So, we have projects where we do the actual fleet management for the customer, right? So, one particular customer, we had a fleet of over 70 vehicles as well as sensors. We managed the whole collection, did that collection across 26 countries, right? So we can scale up and scale down as required by our customer. And we currently collect about 1.3 million miles a year, linear miles of mobile data collection. We also do a lot of aerial data collection. So these are partners of ours that help us with the collection of whether it be a helicopter or a fixed wing or UAS drones. A lot of it is very high resolution imagery and LiDAR. So we just did a collection in San Francisco where we collected high res imagery as well as LiDAR at 200 points per meter. So pretty solid. And then it can be urban and non-urban. So while we collected San Francisco, we actually flew the Muir Woods, the national monument there, just north of the Bay Bridge, and then did analysis and extraction. So every single tree in the Muir Woods National Monument, every single tree was extracted with the height of those trees identified as well. And then we can also perform this indoor and pedestrian mapping. So it's really multimodal. So it can be indoor LiDAR, whether it's via an automated miniature robot, or it could be a wearable or a backpack system. So we can, a lot of different ways we can collect. In the upper right there, that happens to be, you can see the LiDAR point, a colorized LiDAR point cloud, and then the image data from a wearable, a backpack collection we did inside of our building in San Francisco. And again, we operate teams of people that are doing this. We've got teams of between 200 and 100 people that are doing wearables and backpack mapping, not necessarily just inside of facilities, but also outside in pedestrian areas where vehicles aren't allowed. So we have customers asking us to collect data across a pretty wide variety of ecosystems. So just a couple examples. So this is a major global technology company. We did the aerial LiDAR and imagery mapping from a helicopter, looking and collating this dense point cloud collection for them, as well as 3-inch GSD imagery. So we created the DSM, we created the DEM, and then we did a classification and extraction of the features. So it's the buildings, vegetation, utility poles, wires, other fixed obstacles, basically any vertical obstruction, right? And so that was the final deliverable, was that extracted content for them. And then another West Coast technology client, which is a large-scale map data collection across 6 different countries. So, for this customer, we do about 1 million miles collected per year. It's an end-to-end project delivery where we manage their fleet of vehicles. We do the collection of LiDAR and imagery. We do the pedestrian backpack collection, and then deliver that content to that customer. And so we've done US, Canada. Last year we did Australia and Singapore and Hong Kong. We just awarded a contract to do Mexico as well. So pretty global in nature. And again, these are ramped up local employees that we hire in country to help do the data collection. And then the last one is wireless telecom. So in this case, the customer was interested in building a spatial digital twin of their network coverage, both external and internal to their organizational structures, their office spaces. So they wanted to validate signal strength across their coverage geography. So we collected data collection and processing of content and built this spatial digital twin across one of the largest US cities. We then ran signal attenuation and propagation models from their existing 5G assets and created this basically a 3D model one could walk through or fly through looking at signal strength. And then they use that to determine coverage gaps, again, both external and then internal in their office building. So they could see where they had good 5G coverage inside the office space, where they had dead space, where they needed repeaters, et cetera. Okay. So Shelley mentioned earlier, talking about the monies available in the infrastructure bill. And so what I wanted to do is just share this. So if you go to our website, you can see here on the lower right off the voxelmaps.com, and you just click on services and asset and infrastructure mapping. There's a link here to download this free white paper on the infrastructure bill geospatial provisions. So it really kind of defines some areas where you as a user, as a contractor, could look for monies available to help build out the U.S. infrastructure and some opportunities that exist in terms of some business development. So there's please take the time to download that. If you have any questions, you can reach out to me, and there's my contact info. So I appreciate your time today, and we'll be available afterwards in the networking lounge.
Great, Brian, thanks. Two real good, concise presentations. So thanks, you guys. Listen, just real quickly, before we jump over to the networking event, there were a couple questions, but Bill, I think you answered them, and one came in during your presentation, but I thought Brian might have a view on it as well. One was from Pooja Mahapatra that said how geography and location dependent are your AI algorithms? That's one question. But then the other question came in on just leveraging GPS and the real-time GNSS system for kind of centimeter scale accuracy. So I wonder, Bill, one, you might want to say kind of what your views were, and then Brian, maybe you want to jump in on that for everybody.
Yeah, so I jumped in quickly with a pretty short response in terms of the chat, but essentially in terms of the accuracy that we have, it is a byproduct of the resolution of the imagery that we're working with. So when you're working with satellite imagery sort of at the 0.5 meter to meter scale, that's going to be different than working with aerial imagery. One of the advantages that we do have, though, is when we're working with 5 centimeter, 10 centimeter imagery, is that we are extracting all of the features in that stereo view, and then being able to match all of those vector points on top of each other. So essentially we are extracting things 4 or 5 times over and then putting everything together in that vector base map view, so we can actually maximize the resolution on that piece. So that's, and I'm happy to go into more details if we want to go into sort of the separate room.
Thanks. Brian, you want to jump in on that?
Yeah. So I was gonna about the geography and location dependency on our AI algorithms. So we've collected data on a global basis, and so we have an ontology, a library of features that we've trained our algorithms to extract. Now, a light pole in Chicago is different than a light pole in Tuscaloosa, right? And different than one in Antwerp. And so there's some training of the algorithms based on the geographic areas, right? So we have this library, but there's localized training that is required, and I'm sure it's the same for everybody, where you have to train the algorithms for specific parts or features of that feature, right? So it could be, the pole and the cross arm and the lamp itself are unique in different geographies.
Okay.
And I was going to say, I mean, the way we do it as well is a little different, because we do it based really off the LiDAR point cloud. So our extraction is done via 3D semantic segmentation. So we're really not using the image data looking at it. We're looking at the actual physical structure in 3D space to actually create the objects, the training of those algorithms.
Yeah, I'm really excited about that. I mean, that one graphic, Brian, that you show where when you show the entire Earth and then just the grid around it, I mean, that has got to paint a picture for people about how we could start populating these voxels, these spaces around the world with different data. Now, address all the issues that we talked about before, about different data standards or people collecting data from all over and how do people access it. But it's just a wonderful vision as we go forward in the future.
Yeah, it's a good structure to fill.
Yeah. Oh, outstanding.
Infill with
Yeah.
with data from any source, right?
Yes, outstanding. Yeah. And the other thing I really liked was when you said we've got, I think I don't know, characterized it as kind of a piece where you could start to hear sounds. I mean, essentially, as we talk about kind of living in a true digital world or the metaverse, then you kind of want it to be as representative if you're here looking at the machine as it is if you were to walk outside, and we're starting, maybe a long way to go, but we're starting to get there.
Yeah.
So good. Okay, I think we will call this part of the whole session a wrap. So thank you, everyone, going all the way back for the session. I know it's been a long day for everybody. We've had great participants, and so I really appreciate those that are have called in and have given talks, but also asked questions. Brian and Bill, thanks for your time.